Okay, so like I said, we're in the physical evidence side of things, and so a lot of the things that we find um, in a crime scene and comparison objects uh, is fiber evidence. And so we do this from tape lifts and so on, and it has some of the most forensically useful information that we can find. And because fibers, we're constantly shedding fibers. Our hair is constantly coming out. That's why you see in any kind of food prep area, people wearing little caps, or now with these big beards that guys have, they have the little beard thing that looks funny to me. But anyway, fiber evidence is one of the most useful things. Um, Thanks to a few of you who went to the microscopy talk that we had just a few days ago. What'd you think of that? I thought it was pretty good. Yeah, he had lots of interesting examples. And so we're dividing this into two topics. We're going to do biopolymers and natural fibers today, and then next time we'll do synthetic polymers and fibers. And so we're going to talk about the polymer basics, and we'll get into that a lot more on the next talk for sure. And then we'll talk about biopolymers and some semi-synthetic polymers. So things that may start out natural, like natural rubber with an extract, and then it's polymerized. We'll spend a fair bit of time on polysaccharides, all of the different cellulosic fibers that we have. We'll talk a bit about proteins, and then we'll get into protein fibers like hair at the end. Okay. So in all of the polymers in forensic chemistry, we have all these different types, and we're going to focus on the ones in the red box for now. We're not really going to get into DNA, although that's a polymer as well. We don't really use it for its physical shape. We identify the different base pairs and so on, and the frequency of those tandem repeats, and that gives us a DNA signature that can be individualized. But we're going to spend most of our time in the polysaccharides and starches, and then talk a little bit about semi-synthetic polymers like rayon and cellophane. So some polymer terminology we'll begin with. Any kind of polymeric system will start with some molecule that's reactive, okay? And that reactive molecule we call a monomer, mono being one. And then you can have dimers and trimers. And then you get to small numbers, 5, 6, 9 or so. We call those oligomers, just meaning many. And then we get to polymers, which are large. Now, there's really no designated switchover number. Like if it's 10, it's a oligomer, and if it's 11, it's a polymer. We don't really get into that, but when it's just reacted and it grows to the point where it starts to run out of starting material, or you have this competition between growth and nucleation, the start of new polymers or the growth of existing polymers, you get a certain polymer profile. Now, that's something that can be forensically relevant too. I must have discovered the heat in this building. Used to, it's freezing in here. And gel permeation chromatography or size exclusion chromatography are the two techniques that we use to characterize the mean polymer length. We won't really get into that, but that was in the chromatography section. Instrumentation that's sort of an add-on to your instrumental analysis class. The chromatography method would be like gel permeation or size exclusion chromatography. Would give you the mean polymer length, either in mean molecular weight or in number of polymer units. And you get these broad curves. It's not really like this polymer has a particular number of units and you don't have any less or greater than that. You get a really broad polymer distribution or size distribution. And that can be forensically relevant. You can have this mean size, and then you have the standard deviation of those, and you could look at that in terms of forensic relevance. But for the most part, we're talking about the physical properties of the polymer today and its shape and so on. Now we get into how it was polymerized. We can have random polymerization. You can see here maybe you have two different polymers or two different ways of bonding. Like let's look at vinyl chloride. We could have that chloride be on the bottom right, and then on the Y maybe it's on the bottom left. And so we have 3 here like this, and then we have switch over again to the right. So it doesn't have to be a totally different molecule. It could just be the way it bonds on. And so we can have that be random, X and Y. Or you can have different blocks of polymers, like maybe you have the vinyl chlorides be the X's, and then maybe you have some other kind of polymer where you've got maybe a CN group. And so the way these are typically done is you might polymerize or oligomerize the X's first, and then the CN groups in a different pot, and then you combine them and link them together. So this is where you get into the material science side of polymerization, and you have different characteristics based on your different monomers. So we'll dig into that a lot more in terms of the physical properties of synthetic polymers next time. Now, in alternating polymers, some polymers have to be alternating, like in this nylon, where you have a diamine here, and so you have that amine group, and it reacts with a diacid. So in this case, you have to alternate X and Y, because the amines don't react with each other and the acids don't react with each other. I mean, they can, but in this case, we're making amine, acid, and that's an example of this alternating polymer. Now, when we get into the polysaccharides, we're going to see a lot of this branching. So you can graft a new polymer onto an existing polymer, or you can have lots of branching. And so we'll see branching type polymers. And so this different kinds of polymer linkages will have a huge effect on the polymer properties. You can have linear polymers that stack really well. They can crystallize even. And so a lot of times, even like polyethylene, which is a very uninteresting molecule if you think about it, it's just CH2 groups alternating. And CH2 groups are very chemically inert. So how would they crystallize? Well, think about, because the CH2 groups are not really attracted to other CH2 groups. I mean, they're not like hydrogen bonding. If you have OH groups, they can hydrogen bond. And like the amide groups in our proteins, they hydrogen bond. And they'll make beta sheets or they'll make alpha helixes. So really strong and stable structures. But what does a CH2 group have to do with any other CH2 group? They don't really care about each other, okay? But because they're exactly the same spacing, they can kind of zip together like a zipper. So think about a zipper. Each one of those little linkages is pretty weak. And in fact, if you've got kind of an old zipper and it starts to break apart in the middle, it's a real pain because it's hard to get them to stick, okay? But that's kind of what's happening with the crystallization of these CH2 groups, is they can zip together because they're exactly the same dimension. And even though there's a really weak attraction between them, if you get a bunch of them in exactly the same, spacing, they can zip together. And once you form that crystalline domain, it's pretty hard to break it up. And so that will change the physical properties of the polymer. Cross-linking changes the physical properties of the polymer. So you have the polymer chains here, and then you've got links that join those chains together. A lot of the reason that polymers are flexible is because the chains can slip past each other. So I brought in a couple of examples of some flexible polymers. So when we stretch these polymers, those chains are sliding past each other. If I were to cross-link this polymer, it would be more like a glass. It would be really difficult to pull and it might break. Okay, same thing here. These are very flexible polymers. We're able to stretch them, we're able to bend them because those polymer molecules can slide past each other. So a highly cross-linked polymer becomes more brittle. And then we have these types of polymers that show dendritic growth. So a dendrimer is one that has a single starting point and then it branches out. And so this is kind of like, if we let this go, this dendritic growth, it kind of starts to look like this koosh ball. I used to talk about a koosh ball, and I finally went and got a picture of one. I don't know what is the word koosh. I think that's just what they made up. But it's this ball with all of these things. That looks a lot like dendritic growth. Okay. Who's in Dr. Petrokovic's lab? Anybody doing research with Dr. Petrokovic's? Okay. Well, one of the delivery mechanisms for one of her fat-soluble drugs was using a dendritic carrier. And so you've got sort of a built-in micelle that has like a hard center, and then the fat soluble drug could be entrained in that molecule and delivered to the body. And I thought that was interesting research. So let's talk about that cross-linking. How many people have heard about vulcanized rubber and vulcanization? Anybody? Okay. So this is one of the first discoveries that allowed us to change the physical properties of a natural rubber. So we would take tree sap, purify the isobutylene, and we would polymerize it and make natural rubber, which is a very flexible rubber. And then they would mix in sulfur into that compound, and that's where the word Vulcan comes from. Okay, so they'd mix in sulfur and they would heat it up, and that sulfur would cross-link and react with those polymer chains and make a more rigid polymer. And you can see that when it's relaxed, there's no strain on those sulfur rings, all of these sulfur cross-links, and you see that, you know, by joining different parts of the polymer, you have some long flexible regions here, maybe some less flexible regions here. But if you try to pull on that polymer, these cross-links will stop the polymer chains from stretching past each other. And so that's the thing that is called vulcanization. Now we have some of these cross links that are really important in our enzyme systems, and that's actually where the toxicity of heavy metals comes in, because heavy metals will precipitate out or latch onto those sulfurs and wreck the structure of the enzymes. So when you ingest mercury or cadmium or some of these heavy metals, they'll get in and they'll actually wreck the function of your enzymes because of their reaction with sulfur. So we have a lot of disulfide bonds in our enzyme systems, and they're essential for the functioning of that enzyme. Now let's talk about the physical properties. We've discussed the flexibility of polymers, and you've heard of the marketing term memory foam. Okay, the idea with memory foam is you push your hand down in it, pull your hand back, and it remembers the shape, and that's supposed to be good for your sleep, right? Your pressure points, if you're a side sleeper, your shoulder, your hips, and so on. And it's pretty comfortable. I don't really like memory foam because when you try to roll over it, it just grabs you and you can't. But anyway, that's my personal thing. But let's look at the temperature dependence upon this idea of shape memory. So shape memory, let's see right here, shape memory, short-term or long-term shape memory is what we're seeing right there. So we're putting a particular shape into the polymer and then removing the form, and you see that it has memory somewhat of that shape. Now rigid polymers like this, these are fixed shapes. So this is really more like a glassy state. You know, I can't really bend it very much without it breaking, just like glass, right? If you try to bend glass, it's going to break. So that's a way to think about the glassy state. It's not a crystalline state. A crystalline state would have a regular repeating structure. A glass does not have a regular repeating structure. It can be amorphous. And so this glassy plastic here is amorphous probably, and it's somewhat flexible, but it has a fixed shape. Okay. This one does not have a fixed shape. Okay. I can bend it down and it remembers where it was. So this has got long-term shape memory. If I were to heat this up, you can see the temperature scale on the right. If I were to heat this up, it would become more like a gum. It would be gummy, okay, where I could bend it and it would stay. It might eventually try to move back to its original shape, but it would have some short-term shape memory. If I heated it up even more, then it might even lose its shape memory, where I could mold it into like a gloppy mess and it would just stay there. Now, sometimes there are transition temperatures. There might be an actual, what we call a melting point, but a lot of times it just becomes a gum and a sticky liquid. So that's, again, a forensically relevant difference between two different plastics. Does it have a distinct melting point above which it's liquid and below which it's just a flexible thermoplastic? Or does it just get softer and softer and softer without a definite temperature transition? So the existence or non-existence of a melting point would be something that you could look at. And then also we have this glass transition temperature. And so that's what I brought today. to show that we can cool this down, this flexible polymer, and get past the long-term shape memory into a fixed shape where it'll shatter. So I brought the liquid nitrogen so we can take this plastic below its glass transition temperature and turn it into a glass. Some fun stuff here. One thing that's fun to do too is just talk about some of the other things we see. Do y'all remember maybe your grandparents had a percolating coffee maker? Yeah, yeah, and it's a boiling pot. It has a heating element in the middle, and it's got a little stem that comes up, and they put the coffee grounds in the little pan at the top, and it boils down here, and the boiling vapor traps a little bit of the liquid and pushes it up the stem and onto the coffee grounds, and then it drips through, and as long as that's boiling, you'll just keep cycling that water over to coffee grounds over and over and over again. You want stronger coffee, you cook it longer. You want less strong, you cook it less. Okay. Well, that sort of boiling straw effect, you got a vapor, a liquid, and a vapor. It'll push that liquid uphill, and we see that here. When I stick this plastic, which is at room temperature, 298 Kelvin, into 77 Kelvin, it's going to boil. It's going to boil inside this, so that you get a percolator effect, and you'll see liquid nitrogen shooting out of the top here. So this is fun. See it? So that's what a percolator's doing. You want to shoot some at you? Yeah, you can kind of see it. I like the little smoke trails it leaves. Now it'll stop boiling once this gets down to the liquid nitrogen temperature. I'm shooting it in my drink there. Okay, see it quit boiling. So now this is at 77 Kelvin, which is, I'm pretty sure, is below the glass transition temperature of this polymer. So it was flexible, now it's not. Yeah, sounds a lot like this. Yeah, so it's still, no, it's not flexible. It's flexible up here where it's still hot, but there it's not. Okay, so let's cool it down again and try to get it deep in there. Where am I finished? Yeah, glass. Yeah. So, so that's the cleanup. We can pick that up later. Now this is fun. I'm gonna try to pour some into this glove. Can you help? Okay. So let's see. You can hold this with your hands, okay? And I'm going to hold this one. I want you to pour a little bit into this glove, okay? But don't get my finger. Someone stole my other blue glove, okay? Pour a little in there. You've poured stuff before, just a little bit. Yeah, a little more. Okay, that's good. Yeah, so now it's no longer flexible. Yeah. In fact, you can thump the fingers out. Yeah, so that's always fun. Yeah, so that's yeah, so Dr. Zoll's going to go, what's all this glove stuff doing up here? Oh, it was. Oh, yeah, he was up there. Where did this pink come from? Yeah, yeah. So, yeah, so that's fun. Yeah. So those are the physical properties of polymers. You could measure the glass transition temperature for these different polymers, and it would be something that you could, log and say this polymer transitioned to a glassy state at this temperature, and it's a way to tell if those polymers have the same cross-linking ability or maybe it's a block polymer and so on. So that's a physical property of polymers that is diagnostic and comparable between the two. So yeah, and then it once it warms back up, it becomes plasticky state again, which is flexible. Boy, I've made a mess up here. Okay, and then we can play with the liquid nitrogen after class because it's so much fun. If you've never played with it, I'll pour it in your hands if you want. So we can do that. So this cross-linking can really change the properties. This is natural rubber, which we, originally got from sap. I guess they still do get it from sap and rubber trees. But you get this isoprene monomers, and then we'll talk about how we do the polymerization in the next lecture. But this vulcanization, which is where a lot of the black color comes from, we mix in sulfur, heat it up, and it makes, and then they mix in carbon black too. So they put in just some carbon, again, to fine tune the physical properties. And so this is butyl rubber here. Then we get into biopolymers, where the polymerization actually takes place in the biological organism. And there's the most complicated chemistry I've ever seen is carbohydrate chemistry. So we're not going to be able to cover it. I mean, I saw one talk on carbohydrate chemistry, and I mean, I was shocked at how complicated it was. And let me just sort of give you the bottom line here. It's right here. It's this multi-chiral linkages, and every OH group is a source or a location of a possible polymerization point. So think about how complicated that can be. Now, many times it's the 1,4 linkage that we'll see, but every one of those OH groups can undergo a condensation reaction, and you can have incredibly complex structures from these carbohydrate molecules. Now, again, these are carbohydrates, so it's a carbon and a water. Every one of those, notice that. So here's a carbon, and here's a water. And here's a carbon, and here's a water. So every one of those carbons, I mean, even when you have just an oxygen here, you've got, that oxygen is the one that goes with this carbon, and we've got an extra hydrogen over on that last carbon. So, but still, it all adds up to this empirical formula of CH2O. So all your starches, all of your sugars, and all of your celluloses are this base structure of CH2O. And if you have a 5-membered ring, it's like a ribose. If you have a 6-membered ring, it's a glucose. So you have all the different size rings, and you have all of the different ways to link them together. And so here's a bunch of different views of glucose. And again, like I said, it's complicated. And so you have different kinds of ways to simplify your drawings of them, Fisher projections and Haworth projections. And you got, most of them are in the chair conformation. So then you even have those kinds of things. You can have chair and boat, but most of them are in the chair conformation. And if you start here from that oxygen, if you go around clockwise from the top, you have the first carbon here all the way around to the 5th and 6th carbon. And then this 1,4 linkage is a very common one. And you have different ways of those hydroxyl groups either being in the equatorial position or in the axial position. And so this 1,4 prime glycosidic bond, here we've got a 1,4 prime connection. So the 1 on this sugar is bonded to the 4 position on that sugar, and it's a sort of it's an ether linkage, and so when you've drawn those together, you've lost a water. Okay, so it's a condensation reaction. And so in these biopolymers, again, the polysaccharides being the most complicated, we have starches, and under starches we have glycogen, amylose, amylopectin. We have some reactions with some of these sugars that have added amines on there, so you get the chitin and chondroitin, and then you have the cellulose-related ones, where you have hemicellulose, and then you have other kinds of molecules that go with those. They're cellulose-related, so the tree alcohols, the coniferal alcohols, and the lignans. So let's look at all those different ones. So if you put an amine on glucose, and here we have acetyl D-glucosamine monomer. So here's the nitrogen that came on. We made an amine, bonded onto that molecule. And then notice we have an acetyl group. We've acetylated it. So here's the acetyl group that's connected to that amine. And so this is glucosamine. And I know you've heard of that because it's a vitamin, it's a supplement. Okay. You can take glucosamine. Why would you do that? Well, this chondroitin and glucosamine is a structure that's in your cellulose, I mean, in your cartilage of all your joints. And so that's what they say, oh, this will help you with your joints. Whether it does or not, I'm no expert. I have no idea. But I guess the one skepticism I have is just because I eat something doesn't mean it's going to go to my joints. You know what I'm saying? So that's where I haven't done my research. I don't know if it helps or hurts, but just because something's in my joints doesn't mean I need to eat it. It's probably best to get it in my diet, but who knows? I'm not going to go into the whole health and wellness thing because I'm not an expert there. Okay. Now, chitin is also in the exoskeleton of insects and arthropods. Okay. And so that's that shell on your insects. So that's kind of nasty. I don't really like to think about eating this chondroitin and chitin. It's like ground up insect bodies. Okay. Now starches, those are nature's way of storing energy. Both plants and uh, we use them. We eat plant starch. We also store these different kinds of molecules in different ways. And so here's this amylopectin would be sort of long-term energy storage. It can contain over 1 million glucose units. And so you can see all these different clusters where these different monomers are added onto these chains. And when we need to get energy back, we can take them off one at a time and use those in the cycle to make ATP. Okay. And here's glycogen. And you can see this is a highly branched polymer. And that helps you remove those monomers one at a time, because look at how many ends you have. You have all of those ends, and you can remove all of those little starch molecules very rapidly. Okay. All those sugars, I should say. Okay, and rapid storage and retrieval. Now let's talk about the celluloses. So this is a strand again of cellulose. Not only do you have variety in how you can link the monomers together, you have all of those OH groups that aren't cross-linked, but they can provide sources for hydrogen bonding. And so you can make some really strong structures that hydrogen bonded networks of polymers are what we call self-healing. So that's a strange word. How do because if you break a covalent bond, you've created a really reactive center, and it's probably going to make another covalent bond that you didn't want. So if you have a backbone, a polymer backbone, and you break that covalent bond, it's going to be really hard to get it to go back. So breaking the backbone of a polymer is not self-healing. But if you have things on the sides of the polymers that can hydrogen bonds are very easy to break and very easy to remake. Okay. And so that would be what we would call a self-healing polymer. And so all of our celluloses, by their very nature, are what we would call self-healing polymers. Kevlar is a self-healing polymer, but it's a synthetic. And we'll see the structure of Kevlar next time. So our alpha helices and our beta sheets and our proteins are also self-healing because they hold their secondary and tertiary structures by hydrogen bonds. The primary structure is the order of the amino acids, but the secondary structure would be the beta sheet or the alpha helix, and those can be broken because the hydrogen bonds can release and then remade. Now, if it goes too far, then you've denatured the polymer and it's not easy to remake, but small insults can be self-healed. And so these cotton fibers represent some of the purest natural forms of cellulose, containing almost 90% of the polysaccharide. Okay, but these arrangements of the cellulose and other saccharides in the plant cell wall is pretty complex. And so you have all of these other molecules that are in there, and some of them are called lignins, and these are the least well characterized molecules. You see there's lots of aromatic rings, lots of hydroxyl groups, and so it's kind of a combination. You've got some carbohydrate type molecules hooked into aromatic molecules and so on. when you squeeze these out of like wood fibers and so on, you get tall oil or pine oil. And so you've heard of pine sol and these different kinds of cleaners. Some of those are extracts. These are the lignins that have been squeezed out of the plant material. Now the plants, you take these different structures and make it into what we would call a woody plant. You have a really complex fiber. You have hemicellulose, you have cellulose fibers, and you have this matrix of lignins and hemicellulose, which contains all of these complex molecules. So a woody plant fiber is very complex, and it's going to be something that would be probably easy to characterize and be forensically relevant, because you're going to have different macroscopic structures based upon the different plants that it would come from. And so we have this stuff all over us right now. Because where do we live? We live here in the Sam Houston National Forest, and those trees are just belching out these coniferal alcohol. So these are pretty volatile molecules, and they're everywhere. And I know it because I try to do cleaning research in my lab, and trying to get a clean metal surface, you can take it right out of the cleaning machine and start doing contact angle on it, and it'll start out where it'll wet the surface because you've got a bare metal oxide, and water will wet the surface. 20 minutes later, the water doesn't wet as well because these molecules are in our air and they're landing on the surface. Another thing that you can find in fibers, especially like children's clothing and obviously firefighters' jackets, is other additives. And so these would be forensically relevant too. You might have other, sort of non-organic substances added to fibers to change their properties. And one of the properties that we have in some of our clothing, especially pajamas, is fireproofing. And so they can put clay powder in the various cotton fibers. And so then when this heats up, it can create this char coating that creates a barrier between oxygen and the organic fiber. And so these fire retardant fabrics, they have additives that will char quickly and then provide this barrier. Because remember, you need the fire triangle, you need the fuel, which this is the fuel here. You need air, which gives you the oxygen. And then you need mixing. And this provides a barrier to that mixing, okay, and heat. Now, some of these polymers are much more reactive than others. If there's any double bonds or triple bonds left in the polymer, it's going to be a very reactive polymer. But then you can also look at the groups that stick off of that. If it's like a chloride, if you have a vinyl chloride polymer, then that chloride can be reactive. The most reactive would be those carbohydrates where they have the OH groups everywhere. And so you can react colorants with those OH groups, and you can fix the colorants to the organic fibers. So in some dyed fabrics, the dye is just mixed in with that complicated structure. In other dyes, it's a color fixing dye, which actually reacts with the OH groups and can't be easily removed. Now, this is an interesting situation. So we have this cellulosic fiber. So again, it's a carbohydrate. So we have all these OH groups on it. So we've got some long fiber here with this OH group. React it with base and carbon disulfide, and we can make this cellulose xanthate or viscose. It's a gum. Okay. And so you can see that, we still have that cellulose fiber, the R group, and we've created this group here. Now, what have we done? This is uncharged. Now, all of a sudden, we have this negative charge on here. So it's going to be water soluble. So this fiber is now soluble. We can extrude it into solution, and then we can react it with a sulfate salt, okay, and sulfuric acid, we can pull add water, and we can split that back off and get to ROH again. So regenerated rayon, which is regenerated cellulose. So it's still cellulose. We haven't changed the backbone of the polymer. And so this really seems strange. We started with cellulose and we end with cellulose. Why on earth would we want to do that? What have we done? We've changed the physical properties. Okay, so the physical properties of this cellulosic fiber, let's say this was cotton. In order to make a long thread out of cotton, what did we have to do? We had to brush it to align it, and then we had to spin those fibers. And this is what we had to do back in the day. Okay, doing this in an industrial process can lengthen those fibers, untangle those fibers, and allow us to do it with machines. So even though we're not changing the backbone of the cellulose, we're changing its physical properties, more easily aligning those fibers and allowing machines to spin those things and to produce the modern textiles that we have today. Okay. Now, one of the downsides of this is a lot of times when you align all those fibers, you end up with a really shiny fiber. And so even though rayon is the same as in terms of the chemical structure as cotton, the physical properties are something that we may not like. Now, this was popular in the 70s and 80s and all the shiny shirts and so on. And you can look at pictures back in the day and you can see those shiny clothes. And a lot of that shine was from the really smooth surface of the rayon fibers. Okay. And then when that became less popular, people didn't want that shiny look, they started blending in things to take the shine away. And so some of those synthetic fibers will have those additives in it to dull the fiber. And then over the time you wash it, it gets shiny again. You'll wash out those additives and it'll get shiny again. So this is the difference between that natural cotton or cellulosic fiber on top, okay, and then the cellulose acetate fibers, making rayon or even acetylating those different OH groups. And so you can make these synthetic or semi-synthetic. These are semi-synthetic fibers. So this cellulose acetate, we've taken all of those ROH groups and reacted them with acetic acid or acetic anhydride. Okay, and it's a condensation reaction. So we lose the water. What does that do? Well, it takes away a lot of the hydrogen bonding, and it also takes away some of the cross-linking ability. And so you have a totally different physical property and a different, curl to the fiber, different physical properties. Let's make some paper, okay? Let's take wood, chip it up. We can blend in some recycled paper, and this is what we call the brown stock. We pulp it up, and then we take that chemical pulping and we squeeze it. We remove the lignins and we bleach it, and then we can press it into paper, press it into tubes. We can layer it and so on. But there's a lot of sulfur gases. During this process. And so if you're ever in the Northwest, I don't know if we have any paper mills in Texas. I've never smelled one in Texas, but if you're in the Pacific Northwest where I went to graduate school, you smell the paper mills because of that sulfur smell. You're driving along and all of a sudden you're like, whoa, what is that? And you just smell that sulfur dioxide and those different sulfur compounds coming out. So this removing the lignins, this is that tall oil. And I've actually received a couple of contracts with companies to try to characterize some of the compounds in tall oil, trying to characterize their Hansen solubility parameters. Because you saw from all of those aromatics and hydroxyl groups and so on, these are pretty complicated molecules and they might be good solvents. So at this point, there's really not a lot of market. There's some marketed products from tall oil, but there's a whole lot more potential there than has been exploited. And so making paper, squeezing out all of those lignins. That tall oil is a sort of an open area of research. Right now, they get sort of environmental benefits for burning it, and so they will get some sort of credits from the EPA for using it as fuel stock. But it's kind of a lost potential because there's a lot of really good solvent-like molecules in that tall oil, and all we're doing is just capturing the heat content in that. Once we make those paper fibers, again, the OH groups dominate the chemistry. So you can zoom in and look at some of the structures of those different cellulosic fibers. And you can see that this might be forensically relevant. The structures of these different paper fibers and so on would be a property of how they were manufactured. And you could definitely tell the difference between the different fibers. What's going on with these pores? Again, you can get water entrained there, and water is going to be attracted to all of those OH groups. So we really depend upon, with all of our paper towels and so on, and toilet paper, on the absorptivity of these OH groups and holding on to water. Now, some fibers, at least man-made and natural, can be pretty complex. And so these might be some of the most complex fibers that we have, these sheath and core type fibers. We'll talk a bit more about them when we get to the synthetic fibers lecture. Even some companies have put like the letter for their company inside the core in their extruded methods of these fibers. And so these look pretty complex. And you can imagine that if you had this, in your question versus your known, you would be able to identify, yeah, both these fibers have an S in their cross section. That's definitely something that you could compare. But these things are nowhere near as complex as hair. So even our most complex synthetic fibers, even with a letter extruded inside the middle of the core, doesn't come anywhere near as complex as a natural fiber of hair. And so these are the three main parts of a hair: the cuticle, which is that outside piece, the cortex, and the medulla. So pay very careful attention to the medulla because we're going to focus on that. And then also, whether it's the cortex or the cuticle, I don't know, but the cross section shape too. Some hair is more ribbon-like this, and other hair is more circular. And this is a main component of how curly it is. I believe that the flat hair is more curly. You could check me on that. And so we could go and look at the different hairs under a microscope. It helps also to do cross polarization, and we can look at different fibers as well. And so I've got this link. Use the one in the video because the one in your notes is a dead link. This Olympus microscope people, they have some great galleries. And let's just go there. I'll show you what I'm talking about. Okay, good. And they have, again, this is the Polarized Light Digital Image Gallery. It's a great website for you guys to look at. These are different chemical crystals. And so it's pretty amazing at how you get such different signals from the different crystalline substances. Like look at the difference between acetaminophen. We'll click on that. And like caffeine. Completely different behavior under cross polarization. Here's cholesterol. Isn't that pretty? I could look at these all day. If you look at caffeine and nicotine and all these different ones, I mean, you can tell the difference uh, just from their behavior under cross polarized light. Here's the different fibers. So these are different natural fibers. Here's the acetate fiber that I showed earlier. Here's silk. Okay. Again, silk is a natural fiber. And here's cotton. Again, cotton is very curly and it's more ribbon-like. So that kind of supports what I was saying earlier. The more ribbon-like, the more it wraps around and curls up. There's flax, another plant fiber. Okay, here's a mammal fiber, polypropylene. Now it looks like there's structure to it, but that's also just because the fiber wraps around and it's a prism effect. And so at the edge of that fiber, you're seeing more prism than you are going through the middle of the fiber. And so even though it sort of looks like there's an edge, we're dealing with sort of a prism effect here. And then let's look at the hairs, okay? So look at the difference in the animals here. So we've got an Alaskan seal. Notice it's very clear. The medulla doesn't have very many hard structures, okay? We can kind of see a little bit of the cortex structure here on the outside. So it's got some splotchiness to the cortex, and we don't see anything in the medulla. Whereas let's look at alpaca. See, look at the medulla in the middle. It's got hard structures or opaque structures in the medulla. So I think the medulla is very useful under microscopy to identify and compare different hairs. Okay, so the cortex for the alpaca and the cortex for the Alaskan seal, again, they're not that different, but the difference would be in the medulla. Look at the Angora rabbit wool. Look how regular those structures are in the medulla. And again, this is the art of comparison. So you're comparing that hair to this one. You know, this one you can't really see the medulla, but you can see there's some lumpy structure to the cortex on the outside. Here's camel down. It's got some dark structures in the medulla, but they're irregular. Look at the civet. Okay. Again, dark repeating structures. So can you tell that, I mean, hair evidence would be really, really helpful. If you saw this same hair on a question piece of, if a scene, some questioned item, or maybe a tape lift off the carpet, and then you go to a suspect's clothing or house and you see similar hairs, I don't know what a Kalinsky is, but it looks like a weasel, okay? Very unique. What are the odds? And then also the structure of the hair, the curliness and so on. Here's a llama. Okay. Here's a possum. Again, more of a regular structure to the medulla. 60 different species. I didn't believe that. That's crazy. Didn't know that. Here's a skunk. Okay. Regular structure, very dark, very filled in medulla. Here's a squirrel. So different than a skunk. And then you get into rocks and minerals, which we'll have not the next lecture, but the next will be talking about particles and particle characterization. And then that'll be our last lecture for the semester. Woohoo! And then we get to the review for the exam and then the tour of the Huntsville Police Department. We're not going to go to Houston. Um, and I contacted the investigator and he said, yes, we're on for that. So that's good. We just don't know which date. Now, let me say that there's a possibility it would be on the 22nd, okay? But I won't know until the 21st. So the 22nd was going to be our review, but it might be the tour. So everybody look carefully. I want you to pay attention to Blackboard on the 21st, the evening of Monday, the 21st. So if I hear from the investigator, I'm going to send out a blast on Blackboard tomorrow morning, meet at the police department. And then we'll just slip the review and the exam, one period, okay? So that the review will be on Thursday and the exam will be on Tuesday, May 1st. But if the tour is on May 1st, then we'll do the review on the 22nd and the exam on the 24th. Everybody flexible enough to do that? So that's our two choices. The 24th is out for the tour, so we're not going to tour on the 24th. The 22nd might be, and he's out of town. He said, when I get back on the 21st, I'll email you. Well, I would be telling you guys the day before the tour, hey, don't come to class, go to the Huntsville Police Department. So on the 21st, pay attention to Blackboard, and I'll try to, I'll make a big announcement blast and send it to your emails. So check your emails on the 21st. And I kind of hope it's on May 1st, because that's always a big end of the semester and so on. But I could go either way. It doesn't matter. So we're getting close. Let's do a Kahoot and then we'll finish out.